So this thing is whatever Yaroslav told you it has to be. So if you add up all the diagrams, it's got to be, it's a well-defined object, and we're rewriting it in a very particular form in terms of color factor. There's a numerator, and there's a set of propagators. The propagators for any given diagram is just read off by looking at, just looking at the picture, and you know who the propagators are, normal Feynman propagators. The color factor, as Yaroslav explained, you put FABCs and then you sew them together. So the color factor is defined by the diagram, and anything else that's left over, we'll put that in the numerator. And if we are we can make this a completely local object in terms of either, it could be in terms of polarization vectors. This can be written in spinor helicity form, and a set of momenta. Okay, and the key points, we're doing it in terms of these cubic diagrams, only 3-point vertices, and you have to put it in that format if you want to have any kind of correlation between the color and the kinematics, because the color is defined by these 3-point diagrams. If you put in 4 points, it does, it defines like a redundant set. So only cubic diagrams, and what you do is you go through the set of all diagrams, let's say 6 points, and you identify groups of 3. And the groups of 3, you take, say 1, 2, 3, there's a 4th leg. So you put a circle around some piece of it that has 4 legs, 1, 2, 3, 4, including this one. And what you do is you find the partners in the Jacobi identity. The partners are given by cycling 3 of the legs around. So 2, 3, 1, 3, 1, 2. We'll draw a little circle. And the rest of the diagram you leave alone. And if we call this diagram 1, this one is diagram 2, and this one is diagram 3, then we have, just from the color algebra, the fact there's an underlying Lorentz, underlying Lie algebra, there's an identity that says C1 plus C2 plus C3 equals 0. So far, nothing profound. The profound statement, or the first profound statement, is that there is always a way of rearranging the amplitude. So the amplitude is unchanged, but you rearrange pieces, move pieces between diagrams in just the right way so that the numerator satisfies the same identity in one-to-one correspondence to every color identity. Okay, and you just go through and you find this. At 4 points, it's trivial. It's always satisfied as long as you're on shell. Remember, you got to be on shell or none of this is going to work right. 4 points, it just works automatically. Any Feynman gauge, any Feynman diagram will satisfy it as long as you get rid of the 4-point interactions and you absorb them into the other diagrams. Then it'll always work. Whatever your favorite gauge is, even light cone gauge, no problem. It's going to work. Landau gauge, doesn't matter. It's always going to work. But at higher points, it's non-trivial that you can do that. And that requires a non-trivial proof, which I'm not going to show you because it'll take a while to actually go through the proof. And then at the end, you're going to complain that the proof is very opaque. But okay. Let's just accept this as it's been proven in the literature very carefully multiple times. And okay, this seems very amusing, the fact you can do this. And of course, the question is, so what? And of course, I answered the so what. And it's a little procedure. Once you've done this, then this substitution is like saying you go from gauge theory. This is how you go from gauge theory amplitudes to gravity. And this is at tree level. Now, maybe one comment is in Yaroslav's lectures, this was not apparent. He was talking, for example, about BCFW. At the 3-point level, it was apparent. It was at the 3-point level, this is actually trivially true, and then you can feed that into the BCFW recursion relation, and you get gravity amplitudes. Those gravity amplitudes, the way they're organized the BCFW way, not the color kinematics way. But just to point out, either way, you can see there's some relation between gravity and gauge theory, because the building blocks, like how do you build gravity this way? How do you build it through the BCFW recursion relation? You use the fact that the gravity and gauge theory are simply related at 3 points. Here the relation continues to all points, or is obvious. I mean, this stuff is always true. It's just whether it's obvious or not. Okay? So it's a different way of, a different organization than the one Yaroslav was talking about, using the BCFW on-shell recursion relations. Either way, you can generate gravity amplitudes. This has some advantages when you're going to high loops. If you're going to tree level, sticking only entirely to tree level, and you're never going to think about doing loop level calculations, you might as well stick to the BCFW recursion relations. But this is much better for loops. And that's for technical reasons, having to do with the fact that it's organized according to diagrams. And when you're dealing with integrals, which is, you could say, the most annoying part of doing loop level calculations, it's much better to have diagrams, a diagrammatic organization. Okay? So for technical reasons, this is better at loops. Okay? And it's the way we calculate in loop level. Now, so let's just write down gravity. So here's the final answer. If I have that and I've done this, then my gravity amplitude is free. I'd write down, this is the double copy relation, Ni, and let me write it as a tilde, and there's a set of propagators. The tilde just means that these two theories don't have to be the same. They could have been two different theories. And another interesting fact, which I won't prove here, is that you only have to do this arrangement on one of the two copies. You don't have to do it on both. It'll still give you gravity, which is very cool. And that, if you're interested, I can explain in private about that. Now, this construction immediately leads to a question, which is this amazing identity. So let's see, there's h mu nu, that's the graviton, and I'm saying it's something like, or there's some precise notion that it's a product of gluons. That's what we're doing here. And then you look here and you say, okay, there's two states. Here there's two states. That's what Yaroslav was talking a lot about, the plus and minus helicities, two states here. And last I checked, 2 is not equal to 2 times 2. Right? So this construction is giving you extra states. Now, the source of these extra states is not too surprising, because this thing is a symmetric traceless tensor. This thing, I haven't imposed any symmetry on it yet. So I would have anti-symmetric tensor, no surprise there, and I'd have a trace, and that would be the dilaton. So, in fact, the decomposition, if I have, let's do this in d dimensions. So, something else very important. Everything I'm talking about here, it works in d dimensions. And that's, again, very important for loops, because we're going to use dimensional regularization. Okay? So, a mu nu, well, we can count. This has d minus 2 states. This has d minus 2 states. And this you can decompose this simply by writing down the symmetric piece. We'll give it a name. Well, I shouldn't say equals, but let me say it's like, through this procedure. H mu nu, and we can count the number of states there. If you count the number of states in a symmetric, in a traceless symmetric tensor, and you do, it's the little group, the number of states is d times d minus 3 over 2. And then there's an anti-symmetric tensor. Okay, and the number of states, d minus 2, d minus 3, divided by 2, and then there's one guy left over. That's the dilaton. Now this brings up an immediate question. And when we started talking about doing these types of calculations using double copy and so forth, the question we always got from our general relativity friends is, can you get rid of this guy? Because last I checked, the universe we live in, there's no dilaton, or if there is one, it doesn't couple to any, there's no, it has no effect on experiment. So its coupling is either microscopic or it doesn't exist. So we have to get rid of this thing. Now, the question is, how do you deal with this? Because if you can't get rid of this in a convenient and easy way, then the formalism can't be used for the problem of gravitational waves. Right? You get stuck on this, like extra states, wrong theory, not the one we're interested in. I mean, you might be interested in theories with antisymmetric tensor and dilaton, supergravity theories, if you're interested in that, more power to you. This works without any worry about the extra states because you're getting the right states. But if you're interested in doing gravity, like real, the gravity we know and love in our universe, Einstein gravity, you have to get rid of this. Now, the solution to the problem is actually not that hard. So the first point is, if you're looking at tree level, and you're looking at, let's say, graviton amplitudes, then this vertex, let's say this could be either an a mu nu or it could be a phi. This vertex is 0. So it means that this double copy, if you're interested in just gravitons on the outside at tree level, these extra states decouple because there's no coupling. 2 gravitons, let's say I'm interested in 4 gravitons. So here's a diagram I can write down. I cannot write down this diagram, or this is not going to contribute for minimal coupling, in minimal coupling, where this is a phi. Okay, so it's just gone, and you don't have to worry about it. At loop level, on the other hand, so we are going to go to loop level. Then there's a little problem because one graviton, 2 dilaton, that definitely exists. Because just principle of equivalence, right? This thing is a scalar. You can give it a fancy name, a dilaton, but a graviton obviously couples to a scalar, universal coupling, and so forth. That's exactly what you expect. Okay, no mystery there. So you see, if you're looking at a loop, you now have a little problem because now you have unwanted states. The antisymmetric tensor goes around here, the dilaton goes around here, and you get the wrong answer. At least if you're interested in doing Einstein gravity coupled to ordinary matter. So what's the solution to this problem? Well, let's ask a simpler question. Let's for a minute not worry about, let's not worry about loops. Let's look at this problem. Right? So this is matter with a mass. So this is massive. These are both massive. This is like M1, this is M2. So that's where we got the potential. The dilaton has a coupling to the mass. In fact, it's directly proportional to the mass. So this would be an example of tree-level problem, an analogous tree level problem. Okay, now we put in a mass. If the mass was 0, if we're talking entirely massless, the dilaton would drop out again. And so, and also, if there's a scalar, the antisymmetric tensor would drop out. But let's make it massive. So, how do we get the correct potential? You know, I'm not going to do that, but Radu is going to talk about the gravitational potential. And if the dilaton is included, it's the wrong answer. Well, you may remember I said something about the potential. I said that potential, it only comes from the residue. Remember when we did electrodynamics? We're only interested in the residue. So this thing might as well be on shell. So this thing, so if this thing is on shell, the idea is if this is truly an on-shell object, looking at the residue, then we actually have access to the states, because this thing is literally, it's literally this, you know, this thing, and then you sum over states. Right? So this thing is this thing. So separated. Well, if they're separated, I see the state here. And if I see a dilaton, I say, I don't want a dilaton. So you just don't include it. Literally, that's what you do. So let's have a closer look at that. So if you're working in helicity formalism, how do you get rid of the dilaton? And how does it interact with the double copy? Or the antisymmetric tensor, if you don't. If this is a scalar, there wouldn't be, the antisymmetric tensor wouldn't couple, but you know, never mind. Suppose it was there. How do you get rid of this? Okay. And the answer is actually very cute. So let's look at the double copy. So let's look with helicity. So this is one way of solving the problem. If you're working with helicity states, then if we look at a graviton, well, let's see, what's a graviton? It's spin 2, so plus and plus, you know, spin 2, it adds up to spin 2. And that we can think of in the double copy as a product of 2 plus helicity states. Okay, so this is a graviton. Okay, now this guy's a graviton just by parity. Graviton. Both of these are gravitons. Who's the dilaton? Well, that guy's, it's a linear combination, or this plus minus. So let's look at this product. So the antisymmetric tensor, I have to antisymmetrize, or the dilaton, it's the symmetric, you know, I have to take a symmetric combination. But nevertheless, plus and minus make 0, spin 0. Antisymmetric tensor in 4 dimensions is also a scalar, a pseudoscalar. It's an axion at 1 degree of freedom, and it spins 0. So this is the dilaton and axion, and antisymmetric tensor, or 2 form. Okay. So now, there I am, and I need to construct this thing without the antisymmetric tensor and without the dilaton. How do I do it? Well, I look over here, the sum. So it says what I need to sum, it's correlated, right? So I'll write the, this is like the double copy. One copy is plus, the other copy is plus. Or cross the cut, because I'm using outgoing convention. On one side it's plus, on the other side it's minus, just by my conventions. So if I correlate in the sum, so in the double copy, I want to take the left is plus and minus. Okay, and the right, helicities, from the other copy, I have to sum over plus and minus, right? But if I don't want the dilaton, I just correlate it. I sum the helicities of the to be plus plus and minus minus, and I just throw it away. So the way we deal with it is very simple. Don't include it. Okay? It's not very deep. So it doesn't cause a problem at all. And the reason is because we're going to be building up the higher point loop amplitudes systematically using these cuts like that. Right? So then we have access to the state, and we don't like the state, we just toss it or don't include it. Okay? So that's pretty cute. So the resolution of the problem of extra states for this problem, maybe other problems there'll be some confusion, but for this problem of doing the gravitational wave problem, it's trivially under control because another piece of the formalism, another way of thinking about it having to do with the unitarity, meaning thinking about things on shell, which I'll spend some time discussing today how to do that, it takes care of the problem automatically. Okay. Now, maybe a little bit more is, for those of you who are sharp-eyed, you'd say, well, yeah, you can do this at tree level, but what about loop level? Because loop level, we're going to use dimensional regularization. And then you may worry that it's something is complicated. You have some complications because we can't work in 4 dimensions. We can't just do this simple trickery with helicity, and we need now a d-dimensional way of doing it. And you might think that this d-dimensional way is going to get very complicated, but I'll show you some more trickery that makes it very straightforward. And the reason why I'm harping on this point is because it's kind of important. It's that it has to do with the generality of the formalism. Like you're doing calculations, and how general is it? Can you only do certain classes of computations with certain spectrum, like it has gravitons and dilitons, or can you do much more general ones, like maybe you just want the dilaton, can you control that, and so on. So it's because we have the access to the states when we're looking on shell, then it's actually fairly easy to deal with. Okay, now let me just maybe hopefully quickly, hold on, talk about d-dimensions, how it works there. Because it's actually kind of cute how it works out. So let's say instead of working, yeah. For the, yes, it's related to, it's definitely related to that, absolutely. It's related, yeah, it's definitely related to that fact that the bosonic string has these states in it. Okay. Yes, absolutely. Now, this, even though I'm not explaining about fermions, but same trickery works for fermions, double copies, and so forth. Yeah. Is a what? Traceless. My matter. Right, but right. Yeah, I'm having trouble hearing. I can guess what you said, but. Yeah, okay, right. So the issue is, right now, okay, now I understand. Yeah, so the question was about taking out the trace immediately. You know, why do you even have this trace? But the idea is we start from gauge theory, and then we apply the double copy, right? So until we've done that, there's nothing to take the trace out. I'm about to take the trace out. Okay, and essentially that, what I wrote there takes the trace out. So as like we do exactly what you want. It's just we don't do it at the first line. We do it after we've done the double copy, but we exactly are going to remove the trace. And now that you mention that, let's actually make it very explicit. So first of all, let's look at Yang mills or photons, you know, or electrodynamics. Okay, and suppose I have a diagram like this, and I'm sewing. So there's an epsilon, there's an epsilon mu and an epsilon mu on the other side. You know, this is of Q, and this is minus Q, and I need to sew this, right? So we all know that formula, at least, well, if you don't know it, find it in the back of Peskin and Schroeder or Bjorken and Drell. It's a completeness relation for the polarizations, because we're going to sew these things. Oh, this should be a nu, not a mu. And anyway, we want to sew this thing. Okay, and this, and let's make this Q and minus Q. And this has a nice formula. The minus sign just has to do with conventions and the metric and so forth. And then plus Q mu, make it R nu. Oh, this is what's going to be a reference momentum. This reference momentum has the property that R squared equals 0. And then plus Q nu, R mu, over Q dot R. If you know your light cone gauge, you'll recognize this as light cone gauge projector or what appears in the propagator. Okay, and this thing, the reason why it looks this way is it removes 2 degrees of freedom, right? The mu nu indices looks like you're propagating this 4 degrees of freedom. This takes out 2 of them. Okay. And we have Q squared equals 0. Also, Q squared equals 0. It's very important because we need it to be on shell. Okay, so gravitons, what are they? We can do the same thing. Let's call this thing P mu nu. It's a projector. Okay, so the gravitons, you shouldn't be surprised what it looks like, because we have to remove additional degrees of freedom. Rho sigma is equal to 1/2 P mu rho P nu sigma plus P mu sigma P nu rho, and then minus 1 over D minus 2. That's a D. P mu nu P rho sigma. And this is literally remove the unwanted states. Note, I symmetrize. That takes care of the antisymmetric tensor. I just throw it away. And then this thing subtracts out the trace. If you take the trace, if you trace this thing, you will find, like if I do a trace on the mu nu, you'll see immediately that this thing is 0. It just takes out the trace. So I don't propagate it. Okay? Now, at first sight, this looks a little bit annoying because you notice this thing here. So suppose you're doing a loop calculation. You definitely don't want this thing here. This is very bad because it's a singularity. It's like another kind of propagator, right? And then also notice something else, that there's a reference momentum. So clearly, the R has nothing to do with anything. It's some gauge artifact. So we want this to disappear. Okay? So how do you make that happen? Well, at tree level, it's all pretty simple, and I'll show you how it works. But in any case, the argument is the same as for the helicity. So if I slice open the diagram, right, and or I'm going to sew it, right, then it's up to me what I decide this sum over polarization. Do I pick the one for the graviton, or do I pick the one for the antisymmetric tensor, or do I pick the one for the dilaton? My choice, right, because it's sliced open, so I can control it. So if I want to throw away the dilaton, it's very simple. I just use this projector to sew. And then dilaton is gone, antisymmetric tensor is gone. Okay? But you get a little unpleasant side effect, which I want to spend a minute discussing. It's this thing. We don't like that. That could actually be extremely annoying if you go to loop level. Tree level won't be a big deal. So let's have a look. So let's see what happens. So let's go to our case. Well, let's look at a photon. Make this a photon, just to simplify. The arguments will be all the same because the graviton vertex will be two copies of the photon. If I show it to you for the photon, I've shown how things work for the graviton. Okay, so this thing. Okay, we're going to have a look. So let's follow the instructions. So what is this thing? Following the instructions. It's P4 minus P1 mu times minus eta mu nu, and then Q plus, this is Q, momentum Q is coming down here. 1, 2, 3, 4. Okay. Plus, let's make this Q mu R nu plus Q nu R mu divided by R dot Q. Okay, and then let me erase all this here. And then on the other side, the vertex, it's P2 minus P3. Okay? And then this is nu. So what is Q mu times this? Right? So Q is equal to P2 plus P3. So what is P4 minus P1 dotted into Q? So let's say this into that Q. P. So let me pick the other one. Okay. It's okay. Minus P1 minus P4. Okay, that solves the problem. This one is fine to use. Okay, it'll be a minus sign, P4 plus P1. So that's, of course, equal to P4 square minus P1 square, which is equal to M1 square minus M1 square. So that's equal to 0. So that guy's gone, right? And the same argument works on the other side, Q mu against that. This guy is gone. So the thing is, poof, gone. Okay? And the reason why it's gone is because these currents on shell are gauge invariant. So the graviton will couple to the energy momentum tensor, or the photon couples to the current, and those things are conserved. And this is basically current conservation at work, or conservation of the energy momentum tensor. Okay? Yeah.
Only the on-shell radiative degrees of freedom do all the job.
Yes.
But for the potential, it should be the other way around.
Correct.
So how do you reconcile these
Yes. That's a very good question, because we're, in a sense, there's a subtlety in what you said. So the more precise statement is we can reconstruct everything we need using on-shell. That is not the same as saying we are staying on-shell. Okay, so as you know, the potential, that V of R, the place it comes from the Fourier transform of the 1 over Q square, right? So what you really need is the residue of that pole. And that residue you get on shell. But then we don't talk about the potential. We say there's energy conservation, and then therefore the energy transfer is 0, and so on and so forth. So the little sleight of hand, or the subtlety that is that the claim is you can reconstruct everything using only on-shell data. But as soon as we've reconstructed everything we need, then we do things exactly the way in your lecture. Okay? So the key, yeah. So the key, yeah. So we're not going to stay on shell, but we are. All information is contained in the on-shell information. Okay. Now, you might ask another question, which I'm not going to go through in detail, is, okay, at tree level, it's pretty simple. There's a projector, it's against a current that's conserved, you're done. What happens if you try the same game at 2 loops? Oh, sorry, 1 loop, at loop level, right? So let's cut this thing, okay? So we can use the same argument, except, the same argument, under the assumption that this thing has a transverse projector on it. Okay, but so the idea is in the projector, this piece drops out, right? But the problem is, if you're sharp-eyed, you'll notice that if you try to say it'll drop out, you have to worry about what's going on the other guy. You got to simultaneously drop these terms both simultaneously. You have to drop it from here, you have to drop it from here, simultaneously, because you don't want these denominators. And you may worry that they get entangled, that you can't drop them both simultaneously. The only way you can drop one of them is by keeping the other one, because you need the transversality of that in order to have a conserved current. And if you said that, you're basically right. It's a little more subtle, but it turns out, and this is actually very cute, you can use the on-shell conditions to arrange things so that this thing is going to be transverse, meaning I can throw this away, automatically without worrying what's on that leg. And the way you do that is you just use momentum conservation in the right way. And that I should explain privately how you do that, but it's an algorithm that you can continue to use at loop level over and over again. So the basic idea is the same at tree level, except you have to be a little more careful. Okay? And oh, by the way, this is connected. See, if you're very sharp-eyed, let's look at gauge theory. So here's gauge theory. If you're sharp-eyed, you may remember that in the quantum theory, you need Fadeev-Popov-Gauss. And the Gauss are exactly what you need to enforce the physical state projector, right? So you know, if I was too fast, right, and I basically throw away these pieces, let's say, just completely, that's not correct, because there's another term, it's basically the ghost term. There's a ghost. And the ghost is necessary in the normal formulation of Feynman diagrams in order to get the physical state projectors right at loop level. So you know there's some subtlety in what I'm saying. When I go to loops, it's a little bit trickier. Okay? But once we go on shell, then you have freedom of adjusting exactly the precise form of the terms and what you keep or what you don't keep. For example, do I keep a term, let's say here there's a polarization vector, this is, let's say, L. Do I keep a term like this, epsilon L dot L, right? Do I keep it, not keep it? So I have some freedom in exactly how I adjust things. With Feynman diagrams, I don't have that freedom. Okay. Now, I don't want to dwell on this point, but let me just say that there's a nice paper. Okay, since I'm sure you didn't understand what I just said, but let me just point you to a paper on this technical point of how you avoid all this trouble for these light cone denominators. Okay, so now I need to go on to the next topic. Yes. So what we want to do is build loop amplitudes using only on-shell data. And the reason we want to do that is because we know that the on-shell amplitudes exhibit some very nice properties that we can exploit, and they're also very compact. So first, let me just remind you just a little bit about unitarity and the normal formulation of how it's done and what it means. And then I'll talk about a different version of it, the one that we use. So normally the way it's done is you write down the S matrix as nothing happening and then a transition. And then you say, well, this thing is unitary, S dagger S equals 1. And from that, you get kind of a trivial identity of profound importance. 1 minus IT dagger is equal to 1. And from there, you can deduce that I T dagger minus T is equal to twice the imaginary part of T. Okay. Which is then equal to, so this is of course twice the imaginary part, which is of course T dagger T. Okay, so this has just been, it's the same thing. So let's just, okay. So this is the normal statement of unitarity. And what this tells you in perturbation theory is something very profound. And it's at the heart of what we exploit, is that once you know the tree amplitudes, you automatically know something about the loop amplitudes, right? It says, if you organize this according to perturbation theory, you'll notice there's 2 of these, right? And here there's 1 of them. So on this side, for example, let's put in some coupling. So there's a coupling G. I'll make this, G to the 4th. And on this side, G square, G square. So this is a statement that if I have a loop amplitude, okay, and I take the imaginary part of this loop amplitude, it says that, if I just read what this says, it says that this should be, well, there's some implied, there's like matrix multiplication, so it's a implied sum over all the states. So I'll call it d-lips, Lorentz invariant phase space, so I'm running off the edge here. Let me continue across that border. And then I would write, this would be a tree level. So this, let's say this side, for example, it's one loop. So in terms of, let's say, diagrams, you can put a g on every vertex. There you go, it's g to the fourth. On this side, see, there's a diagram like this. There's a g and a g. Okay, and the same thing here. So it's a relationship. Okay, and it's a relationship between loop level and tree level. Okay, and it's just a statement. Once I know tree level, I know something about loop level. Okay, and that's, you could say, essentially what's underlying all this. And this, what I'm telling you, was known, in the 1930s. It's quantum mechanics. So this part is, you could say, very well known. Okay. Now, how do you exploit this? Okay. Now, there are mechanical ways, they're called dispersion relations, that you can take this information. Once you know the imaginary part of a function, then using Cauchy's theorem, right, the source of all magic, you can essentially reconstruct the entire function. But that's not exactly true. I mean, there's little pieces that are missing, and those pieces are actually quite important. And just to give you a little example, suppose that the amplitude, oh, by the way, I got to put in an extra minus I, because the conventions, this is the standard way that the S matrix and the T matrix are written, and it's off by an I compared to Feynman diagrams. So I need to take the I out. So if I didn't do that, then imaginary and real are confused. So I'll just stick in an extra minus I. It's just a small bit. So suppose I have, for argument's sake, the amplitude looks like this. A, and then log of, let's say, minus S plus 3. And maybe there's a constant in here to get dimensions right. Okay? Or some dimensionful thing, but that's not important. Now, this thing, for S greater than 0, so there's a physical particle here. Right? If there's no physical particle, there's nothing there. But this is a statement about physical particles. So if there's a physical particle here, S greater than 0, you say, look at that, and say, well, oh, gee, there's an I pi there. I have to analytically continue and so forth. So I'm going to get that this is A log of S absolute value, and then plus an I pi, and then plus, let's say, 3b. And, okay. Now, Cauchy's theorem, is a systematic way of doing it, but it doesn't take a genius to say, look, if I've got an I pi here, right, so that's the imaginary part, I know it came from a branch cut of a function that I should be able to reconstruct. These two are correlated, and notice also the A, the coefficient, is the same. If I know the I pi, there's some way to figure out what the logarithm is. But you may notice another little problem. Suppose the answer is plus a rational function that has no cut, no branch cut. Then you cannot reconstruct it, right? Because it's got no imaginary part. Okay, and that has something to do with what are called subtracted dispersion relations. That's a way of saying that there are pieces that you can't reconstruct. Now, if you're going to use this to, let's say, do some kind of idea of unitarity, building, basically you want to build loops from trees, you can't be dropping pieces. You got to get all of it, right? That's a very important condition. Okay. So the question is, how do you do that? And the solution to that problem is actually fairly simple. Maybe I should add one more problem. So suppose you're trying to reconstruct a 4-point function using this analytic information, the imaginary part, and then you try to reconstruct it. You can do that at 4 points. And there's a whole formalism for doing it. There's something called Mandelstam double dispersion relations, allows you to reconstruct at 4 points. But you immediately run into a problem if you're interested in higher points, because let's look at a higher point. Let's say I'm trying to reconstruct. Let's say we're talking about 5 point, right? 4 or 5. And you count the number of channels, like how many channels are there. By channels, I mean like this is an S45 channel, and there's an imaginary part, and then you go through, and you do the counting. It's 4 times 5 divided by 2 is 10 channels. Okay. There's no formalism for doing that. If I have all the analytic information, how do I reassemble it? Right? And as far as I know, that problem has not been solved. At least not directly. Okay, so we don't want to just do 4 points, we want to do n points. We want to have a general formalism for doing all sorts of problems at loop level. So you need a way to do this reconstruction first that drops no pieces. That's the first condition. And the second condition is it's got to be general. It's got to work in any case that you could think of. Pretty much any case you can think of. Okay. Now, in the 1960s, people, spent a lot of time on this, but they were missing something very important, which you'd have to wait another 15 years before you had it. You had to know something about the dynamics. Like a QCD, you had to know the QCD Lagrangian. You had to know something about what these functions look like. And that information only came later. Once you know something about the interactions, you can go back to this and say, how can we improve? Okay, and there's one other little important fact about how you might want to attack this problem, is as you go to harder problems, like higher and higher loops, more and more legs, the integrals become very hard. Okay, so whatever you do, it needs to be compatible with the way that people know how to do integrals. That's another constraint. You can have a beautiful formalism, but then if it's hard to use or you don't know how to use it to actually do calculations, you're in trouble. So you need a formalism that's compatible with great advances in doing loop integration, which, by the way, I won't discuss here. That would be a topic for, I don't know, it'd take a while to explain what the modern way of doing integrals. But let me just say there is a way of doing Feynman integrals that's extremely powerful because it's been built up over the years. So you'd like to reformulate this, all of these ideas, in a way that everything is turned into ordinary Feynman integrals, which we know very well how to do now. Okay, and the answer is work at the integrand level. Don't try to reconstruct the functions after integration. Try to reconstruct what your Feynman integrals are before you integrate. That's the basic idea. Okay. Now, let's pick an example. So I'm going to pick the simplest example I know, which is n equals 4 super Yang-Mills. And you guys are saying, gee, that sounds pretty complicated. It's all this supersymmetry. Well, we don't need to know any supersymmetry. The only thing we need to know is the spectrum. And then we can march forward and I'll work out an example of how these ideas are put together. What this means. So I'll explain by example. And it'll be n equals 4 super Yang-Mills. You've heard a lot about it. It's in the Mulder-Sena conjecture. It's an off-shell version doesn't. Off-shell superspace doesn't exist. And superspace is complicated, and so on and so forth. Never mind all that. The only thing we need to know is the spectrum. So we're going to look at amplitudes with 4 gluons. Actually, there we go. We're going to do n equals 8 supergravity while we're at it. Double copy, so it'll be simple. So the idea is, if I'm interested in 4 gluons, and let's talk about one loop. So 1, 2, 3, 4, these are gluons. In here, can circulate any state of n equals 4 super Yang-Mills. What is it? There is 1 gluon. There are 6 real scalars. And we can put 4, well, we can make a Majorana. Okay, so we don't need to know, for this problem, we don't need to know anything about supersymmetry. Because how does a gluon couple to a gluon? Well, we know. How does it couple to a scalar? We know. How does it couple to a fermion? We know. Right? It doesn't involve supersymmetry. Right? The coupling of gluons to any matter is just dictated by gauge symmetry, or Yaroslav would say little group scaling. Okay, so we know all these interactions without worrying about the details of n equals 4 super Yang-Mills. So we're actually going to do it in components. We're just going to add this up. There are much better ways of doing it using a non-shell superspace, but that's not so important for what I need to show you. Okay, so what we are going to do, it's very simple. It's kind of like right here. We're just going to cross this out. There we go. We're going to build this thing, but we're going to ignore the integral. All right, that's what I mean by integrated level. So it's the same as you see in the unitarity relation, except we're leaving the integration for later. Okay, so what time is it? Oh, I see I'm running into trouble with time. But anyway, let's march forward. So Yaroslav gave us what we need. So what we need is the sum over states of this. 1, 2, 3, 4. Okay, let's use helicity. I'll make these minus, minus, plus, plus. So that'll be the first example. Okay, and we're going to just follow what Yaroslav is doing. I'm also, I want to tell you up front, I'm a sleight of hand because we're supposed to really be doing dimensional regularization, right? So I'm going to use helicity. So you say maybe there's something wrong, but at least in this case, there's no worries. This is going to be the exact answer you would get if you did do it dimensionally regularized and so forth. Yeah. But anyway, let's just work it through. It's a nice example. So Yaroslav told us. Let's see. He said, for example, he said plus, and then plus minus, and then plus. He said that's 0. Right. So and these are gluons on the outside. See, these are gluons. Now, I don't know if Yaroslav said this, but he definitely implied it. If I make it scalars, that's also 0. And it's basically little weight, the little group weight, that you can't write anything down that has the right dimensions. It's what Yaroslav explained. And then there's one more, so we can do plus plus, and then fermion, that's 0. Okay, but don't worry, there's non-zero things. And then Yaroslav also wrote down Park-Taylor. He said, for example, plus, now we should put some labels. 1, 2, I don't know what labels I should. I don't want to use 3 and 4. Let me use 5 and 6, for example. Then this is minus, and this might be 5 and 6. Or maybe I'll just relabel it when I need it. Okay, 3 and 4. How about that? And let me write it in the same, exactly the same way he did. Okay, there's I, there's 1, 2. Make that 3, 4. Let me actually reverse this to make it, just to write it exactly the way he wrote it. Okay, so let's make this 1, 2 to the 4th, 1, 2, 2, 3, 3, 4, 4, 1. Okay. Okay. So let's look at this thing here. So let's evaluate that. So this is a product of 2 tree amplitudes, and the pieces are to be found here. Let's make this, there's 1 minus, 2 minus. Okay, there's, let's call this one L1. Let me call that guy L4. Okay. So these legs are all on shell here, right? So 1, 2, and then 3, 4. Okay, so who can propagate? Right? Suppose I put a scalar in the loop. Also the parity reversed. You know, all of these statements, if I make it minus, minus, scalar, scalar, that's 0, minus, minus, fermion, fermion, that's 0. Okay. So the fermions and the scalars can't propagate because the amplitude is 0. So the answer is 0, except right here. Suppose this is now a gluon. Okay, so L1. Okay, maybe I should call that L3. Okay, so if this is a gluon, everything's okay because you see there's an amplitude here, there's an amplitude here. Remember, across the cut, you have to reverse the helicity because we're using an outgoing notation. Everybody's outgoing, so if it's outgoing, then it becomes, well, if you continue to be incoming, but then we want to flip it to be outgoing, so you flip the helicity. So it's the same gluon. Okay. So both of these are non-zero, and it's the only contribution. And in fact, it's the same in QCD. It's the same in any gauge theory coupled to any massless matter. You'd have exactly the same situation because fermions don't contribute here. Now, don't panic. The fermions are going to contribute in a different channel when you look at another channel. Okay? Oh, and I should have, of course, mentioned this. I'm using color ordering, color ordered. Right, that's what I'm writing down. You notice there's no like color factors here because it's all color stripped, color ordered. We just have to maintain ordering of legs. So now I can write down the cut very easily, where the cut is now defined to be the old cut, but I ignore the integration. Yeah. Yeah, so these are gluons. Oh, except, yeah. You know, these are gluons and only gluons because they're the only ones where you get a non-zero amplitude. Okay? So I can now write down the answer for the cut. Okay? So the cut, we'll call it cut. See, this is the cut. And what the cut means, product of amplitudes summed over states. And ignore that phase space integral. So I write it down immediately. It's 1, 2 to the 4th. Okay, and then I have to look here. It's L1, 1, 1, 2, 2 L3, L3, L1. Okay. So that's one side. And then on the other side, oh, I need some minus signs. Well, I'm going to be a little sloppy, and I'll quote Yaroslav. The minus signs disappear. They all cancel out, so you don't have to worry about them. So you have to worry about the direction. So you see, if this momentum is incoming, it's minus L3. Right, so you should really track it. So if you're an honest person, I'm a dishonest person, I'll just ignore the minus signs. And then I'll tell you, don't worry about the minus signs, they're all going to cancel. Okay? And Yaroslav mentioned something about that. So I'll just be sloppy and ignore the minus signs. And then at the end, they all drop out anyway. By the way, if you're doing that for fermions, then those minus signs do matter. For bosons, life is good. These minus signs on the direction of the momentum, right? I should have, like, there's a minus L3. There it is. Well, this is incoming, so it's a minus L1. This should have been minus signs, right? Should have been a minus sign there, but never mind. They're all going to cancel. Okay. Okay, L1, L3 to the 4th, and then L1, oh, it's L3, 3, then 3, 4, then 4, L1, and then L1, L3. And this is the answer. Okay? This is the value of that cut. Now, I see I'm running out of time. Now, the way it's written right now may look a little unfamiliar because these denominators, they look a little unhappy, right? They're spinor products. To make it a little more familiar, we want to turn them into Feynman propagators. So how do you take one of these spinor products and turn it into a Feynman propagator? Remember, these are all on shell. And of course, the answer to that is, what we do is, for example, L11, this guy, we write it like this. L11 divided by L1 dot P1. Oh, actually, I should have had a minus sign there. Okay, and this is just using the fact that AB, BA is equal to 2 PA dot PB. Okay, oops, B, that's a B. So, so Yaroslav, I'm sure, explained that in great detail. Okay, so this thing, it still doesn't look like a Feynman propagator. Okay. But let's fix that. So we can rewrite using on-shell conditions. Remember, we're working on-shell. We can rewrite it as, and let me call L1, let me call that K. Right, so it's K minus P1 square. Good. So that guy is a Feynman propagator. Right? Which Feynman propagator? So let me just draw like a box. Okay. So this is P1. That's P2, P3, P4. This is K. And this guy, this momentum here, so let's make K go like that, is K minus P1. P1 is outgoing. All these are outgoing. Okay? So you can easily convert all of these into Feynman propagators that you can then recognize. If you go ahead and do that, and I'll quit in just a second since I'm running too late, but let me at least get to a punchline. If you do that, you can reorganize the cut. So now it's algebra. Maybe it sounds like a homework assignment. 1, 2, 3, 4, minus, minus, plus, plus, times a numerator, which I'll show you in a second, divided by 2 Feynman propagators, P1 minus K1, but they're raised to a high power, P2 plus K2 to the 4th. This is what you get, and this n tilde what the n tilde is L11, 14, 4L1, okay, L1, L3, L3, 3, 3, 2, okay, it gets a little empty. Okay, whoops, wrong one. That should be an angle. And then 2L3, we're almost done, and then L3, L1. Okay. You'll notice this matches that. This is a trace, which I'll define in a second what that is. And it's basically a trace L1 slash P1 slash, et cetera, going all the way to L3 slash, just following. And this trace plus is defined to be, let's say trace plus of something is defined to be 1/2 of trace 1 plus gamma 5 with whatever is there. So it's an ordinary type of object you've encountered when you're thinking about fermions. Okay, and this looks a little daunting, but you'll see it's very easy to evaluate. So we'll do that next time and to discuss that. Now, the reason why I'm doing this, actually kind of important, is because I want to show you how it works in practice. How do you actually go about doing a calculation and extracting results by gluing these amplitudes together? Okay.
All right, so we have time for one quick question, maybe. Anyone have a question? Your questions are not quick. Maybe the student first.
I'm still a little confused about how you're proposed to get the full loop amplitude just from its imaginary part.
Well, the trick will be that we are going to do something very slick, because we're not, you see, in the old days, well, I erased it there, they're thinking there's some arbitrary unknown function, and we have to reconstruct this arbitrary unknown function from its imaginary part. And then that causes trouble because you don't really know exactly what this function is supposed to be. And in fact, it has pieces that don't have imaginary parts. The way we're going to do it is going to be, we know that these things came from Feynman integrals. And we're going to use that information to fill out missing pieces. Okay? And it turns out, on top of that, in the context of dimensional regularization, there are no rational parts. And that little amusing comment, everything has an imaginary part. So you can actually always do the reconstruction. And that I can explain. So you're using, in order to properly do this reconstruction, the main thing that you're using is the fact that it's not arbitrary. It's a definite set of functions that we know what they are. They're things that come out of Feynman integrals. And then we take advantage of dimensional regularization to help make sure we don't lose pieces.
Okay. Is it going to be quick?
I'm thinking about your relationship about unitarity and three graphs. So you get the S matrix on shell by just know all the sets of the three graphs. Is that correct?
Okay, sorry, I couldn't.
I'm wondering how to recover the full-fledged field theory from the three graphs through unitarity relationships.
Yeah.
You wrote that relationships of three graphs are equal to the imaginary part of the S matrix.
Right.
So, loops.
So,
but your loops, the external lines are always on shell.
okay.
This X matrix is defined as an on shell object.
Yes.
The question, how to get off shell? It's possible to have some model where from the on shell S matrix elements you could
The
get
key,
the
yes. Okay, so the question, it's similar to the previous question, because it looks like I'm performing some feat of magic that if you have a function and you only know its imaginary part and there are rational pieces, you'd think you can't reconstruct it, because you can't get something from nothing. So if something doesn't have an imaginary part, you can never figure out the associated real part. That's the problem. But we're not trying to solve the problem of arbitrary functions. How do you do the reconstruction? We're trying to solve a specific problem. Imagine that, or not imagine, we know quantum field theory, we know QCD, we know the Lagrange, we know the Feynman integrals, so we know a lot about the functions. So we're going to sneak in some extra information from the fact that we are supposed to get Feynman diagrams. So in a sense, what we're going to, the logic is you reconstruct the integrand that you would have gotten from Feynman diagrams, but organized in a very different way. And you're using it with on-shell data. And the way you get from the imaginary part, you get the real part, is in the context of a Feynman integral. There's definite relations, or things come together, things belong together. It's not some arbitrary function. Okay, and there's various theorems of how, the basis of functions that Feynman diagrams give you that allow you to make sure you don't drop any pieces. So this is non-trivial. So in fact, your question is a very good one, because it looks like we're doing something that we're not allowed to do because, basic complex variable theory. But those ideas, the general idea of how do you reconstruct functions, if you know something about the function, you have a big advantage. And we know that all these functions had to have come from Feynman diagrams. Yeah. That's the key part. There's maybe one other comment. So, you look at the way I'm doing it, and if you're a reasonable person, you might say, well, look, for this problem, why are you doing it this way? Just use Feynman diagrams, right? And indeed, for this problem of 2-to-2 scattering at one loop, you don't need any of this stuff, okay? But the key point is this now gives us the power to do all sorts of really complicated problems. And the first of these, where these ideas were applied, was doing n equals 4 super Yang mills, and then n equals 8 supergravity, but doing arbitrary numbers of legs. That you cannot do by Feynman diagrams. This way you can generate expressions for extremely complicated situations, infinite number of particles or arbitrarily large numbers of particles, and you can reconstruct the entire function and get the exact expression. Okay. So analogous to Park-Taylor, except now it's at loop level. Okay.
All right, so I remind you that before going to the coffee break, we need to take a group picture downstairs. So let's thank Zvi again.